When we look at geographic data, a map of disease outbreaks, crime rates, or housing prices, our eyes naturally search for patterns. We instinctively group glowing dots together, seeing clusters and trends that seem to spread organically across the landscape. But human intuition is a flawed analytical tool. What looks like a distinct cluster on a map is often just a trick of proximity. Visual closeness does not automatically equal mathematical significance. To prove these patterns are real, researchers traditionally turn to standard statistical regression models, attempting to quantify the relationships between variables across different regions. These traditional models fail for a very specific reason. They are built on the assumption that every data point is independent. They look at this linear regression line and treat a neighborhood in Manhattan exactly the same as an isolated town in Wyoming, entirely ignoring the physical geography where that data originated. This ignores Tobler's first law of geography, which states that while everything is related to everything else, near things are more related than distant things. A foreclosed home affects the property value of the house next door. An infection in one county easily crosses the border into the next. When you apply independent statistics to dependent geographic data, the resulting math is invalid. To accurately evaluate geographic phenomena, visual intuition and basic statistics fall short. Researchers require a specialized framework designed specifically to quantify spatial dependence. GeoDa is a purpose-built, open-source software engine designed to solve this exact problem of spatial dependency. It operates through a methodology known as Exploratory Spatial Data Analysis, or ESDA. ESDA serves as the bridge between rendering a static picture of a map and executing rigorous mathematical modeling of the space it represents. GeoDa achieves this through a signature capability called linked brushing. As a user interacts with a specific data point on a statistical graph, the corresponding geographic polygon immediately highlights, creating a real-time connection between raw data and the physical map. By selecting points on the scatterplot, a researcher can instantly isolate statistical outliers and see exactly where they exist in the real world. While this interface is highly interactive, the software's actual utility lies entirely under the hood, within its mathematical operations. GeoDa takes visual geography and translates it into a strict mathematical framework, giving users the tools to definitively prove spatial dependencies. Before running any statistical test, we have to solve a mechanical problem. How do we mathematically define a physical neighborhood for a computer algorithm? The answer is the spatial weights matrix. This is the mathematical bedrock for all operations within GeoDa. The matrix takes irregular geographic borders, abstracting them into simple geometric shapes. The software calculates their centers, establishing anchor points. GeoDa then maps relationships by calculating contiguity, identifying which shapes share borders. This visual network transforms into a machine-readable binary grid of ones and zeros. Depending on the research parameters, this matrix can also be constructed using distance bands, defining neighbors by a specific radius rather than a shared boundary. A computer algorithm cannot look at a map to understand proximity, but it can read this matrix. The spatial weights matrix serves as the vital translation layer, converting physical topology into the relational weights required to run advanced spatial statistics. With the physical world mathematically mapped, GeoDa can begin executing its core diagnostic tests. The first step is to check for global spatial autocorrelation, measured by a statistic called Moran's eye. This Moran's eye scatter plot evaluates the dataset in its entirety. It determines whether the overall system exhibits clustering, dispersion, or total randomness. But Moran's eye has a strict limitation. It can prove that clustering exists globally across the dataset, but it cannot tell you where those clusters physically exist on the map, and calculates localized scores for every individual polygon. A high-high cluster, shown here in red, means a polygon with a high value is physically surrounded by other polygons with high values. This proves the existence of a localized hotspot. By applying significance tests to these local scores, Lisa strips away random visual noise. What remains on the map are only the clusters that hold up to mathematical scrutiny. For epidemiologists, this is the difference between randomly scattered illness and a mathematically validated vector of disease spread. For city planners, it means verifying localized crime patterns to precisely allocate municipal resources where they are statistically proven to be needed. LISA operates as an objective truth teller in spatial analysis. It mathematically validates what the human eye only suspects. Identifying existing spatial patterns is only half the equation. The next step is building predictive models that account for that geographic influence. This is the standard equation for ordinary least squares regression, and it fails here because it cannot account for neighborly influence. If you apply this equation to spatial data, it severely skews the predictive outcomes, leading to flawed policies in urban planning or economic forecasting. GeoDa corrects the structural flaw through spatial regression modeling. The software modifies the regression equation, forcing it to factor in the spatial weights matrix we built earlier. It inserts a spatial lag term. This new variable specifically represents the calculated mathematical influence of neighboring areas. This updated mathematical model accurately distributes the weight of geographic influence across the entire dataset. Spatial regression ensures that predictive modeling respects the reality of physical borders and proximity, neutralizing the risk of autocorrelation bias. GeoDa is not a cartography tool. It lacks advanced map editing capabilities and drawing features. Its identity is strictly that of a statistical processing brain, built to slot efficiently into a larger geospatial software stack. A standard workflow involves feeding clean CSV or GeoJSON files from a spatial database into GeoDa for processing. The mathematically validated outputs are then exported into software like QGIS or ArcGIS for visualization, or passed to Python and R for further programming. This workflow highlights a critical limitation. GeoDa relies absolutely on high-quality, pre-cleaned spatial datasets and carefully validated coordinate systems. If the geometric data fed into the system is flawed, the spatial weights matrix will fail, corrupting all downstream analysis. The demand for perfect spatial data is only increasing. Industries are aggressively scaling up to handle massive datasets and automated AI analytics. As engineers construct real-time digital twins and intelligent smart cities, the foundational spatial mathematics that GeoDa relies on become more critical. Automated systems require perfectly sound mathematical rules for geographic interaction to function effectively without human oversight. Mastering GeoDa equips a professional with the necessary technical capability. It moves the user beyond treating geography as a static picture, allowing them to command it as a dynamic, mathematically proven system.